So question 1, we have 2 particles with positive charge here and 2 with negative charge, and we have a positive charge particle P here on the y-axis, and it's saying what is the net electrostatic force on the particle. So the electrostatic force comes from the direction of the field on the charge, so we have to work out what the kind of resultant field is from these 4 charges upon P. So field, electric field, goes from positive to negative. So we have radial fields coming out in all directions from the positives, like that, and we have radial fields coming in to the negatives as so. And so what we need to do is we just have to isolate the direction that passes through P each time. So for example, if I take this one here and cross it through P, like that, we know that charge goes from positive to negative. So the field line is through like that direction. So if it was just this charge and P would move along that line there. However, we have 3 others, so I'm going to do the same thing. Now you would do this with a ruler in the examination, like that, and then we have 2 more. However, they're coming from positive into the negative, so we're going in that direction, and then again through P, like that, in that direction. So we can actually see that this is a line of symmetry, which is nice of them. So we've got kind of this one and this one, and this one and this one. So the resultant of this one, this one, this one, this one is direction D. So the answer is D. Question 2, we have a hot air balloon, and it's at a height h above the ground. So we have a hot air balloon at height h above the ground, and it's stationary, so it has 0 velocity there. We're dropping an object, so the object is released from that position, and then it's going to accelerate due to gravity down towards the ground. Now that's kind of situation 1. Situation 2, we have a hot air balloon that's at the same height above the ground, but this time it's actually traveling upwards. So if it's traveling upwards, when we release the object, that object too will have velocity v upwards. So for a short while, it will actually rise up until the acceleration due to gravity drops the velocity to 0, and then it will accelerate down towards the ground. So we can actually see that the distance s from here to here is shorter than the distance s of this one. So s has increased, therefore the time it takes to hit the ground has increased because it's traveled further. We can see that actually when v reaches 0 here, it's higher up, so it's going to accelerate for longer than that situation. So the final velocity has increased. The only thing that doesn't change is the acceleration due to gravity. So acceleration is constant, so it's D. Question 3, we're looking for the magnitude of impulse. So impulse is the change in momentum, and the only difference between it being magnitude is if we're looking for the magnitude, if the change of momentum works out negative, we just ensure that we remove the negative sign. So we treat it exactly the same until the final step, where if there is a negative sign, we remove it because we're just looking for the number, so to speak. Okay. Right, so we have a particle that is a ball that's moving with mass m and travels at speed v before the collision. Notice how they're saying speed here. before the collision, and its speed is v. When it has collided and it's on the rebound, it's lost 75% of the initial energy. So the kinetic energy is half mv squared. So if m is m and v is v, then the initial, kind of beforehand, the kinetic energy is half mv squared. Now afterwards, it has lost 3/4 of it. So as we have the half in a fraction, I'm going to put this into a fraction. So it's lost 3/4. In other words, a quarter remains. So remaining, we have a quarter of the initial, which works out as an eighth mv squared. Okay, so we had a half mv squared before, an eighth mv squared after. So we can see that, hopefully, you can see that 4 of these go into that. Okay, so what we have is the v squared, because the m hasn't changed, but the v has changed. The v squared has divided by 4 to produce an eighth, because we've done a quarter of it. Therefore, if we find the square root of v squared, we get v has gone to v over 2. So on the way back, we have a particle with m, and its speed is now v over 2. So the change in momentum is the final. Okay, so the final, so we're going the other way. So it's negative mv over 2 minus the initial, which is mv. So we have minus half mv minus a whole mv. So that's minus 3 over 2 mv. And then at that point, I would pull that out, sorry, and say it's that. So it's D. Question 4 asks for the efficiency of energy transfer in a system. So we have a cyclist who is riding up a hill, and that hill has a vertical height of 100 meters, and the cyclist does it in 500 seconds. The cyclist's mass combined with the bicycle is 80 kilograms. And we know that the power developed by the system is 200 watts. And we need to know the efficiency. So we need to know how much power it actually took to do this, and then divide that by the 200. So we know that power is energy divided by time. And I can see here I've got a mass and I've got a height. So I'm going to go with gravitational potential energy. So it's mgh, and then divided by, the cyclist does it in 500 seconds. So if I just clean this up, I've got, so 2, 1, so I've got 160 watts. Okay, so 160 watts. So I have my efficiency is 160 divided by 200, which is 80%. Again, the answer is D. Question 5, we have an ideal gas. Now, the thing to note about an ideal gas is it must be in Kelvin. All right, so the answer must come from a calculation in Kelvin. So if you didn't recognize that and you plugged in 30 into a calculation, then you would automatically have an incorrect answer. So we have the ideal gas equation. Let's say it doesn't really matter which one you use. You could use NKT, you could use nRT. And then what I like to do is I like to remove the constants. Okay, so I'm going to just scrub out the constants. When we've got some sort of ratio in a paper 1 question, just remove the constants. You don't need them, and it just cleans everything up. It makes it look neater. So we have PV equals T. Now I know that's not correct, but honestly, it will make everything a lot easier to figure out. So we're just changing the variables. Okay, so initially we have an ideal gas with pressure P, volume V, and a temperature of 30 degrees Celsius. So PV equals 30, but we need to convert to Kelvin. So 30 plus 273 equals 303 Kelvin. Okay. All right. The gas is compressed to, so that's the first situation. The gas is compressed to V over 6, and its pressure increases to 12p. And we need to know what happens to T. So 12 over 6 is 2, so we have 2 PV equals the new T. So PV equaled 3, sorry, I shouldn't have done that. PV equaled 303, so 2 PV equals 2 lots. Of 303, which is 606 Kelvin. Now that isn't D, that's in degrees Celsius. So we need to do 606 minus 273. My maths is terrible, as those of you that I teach will agree. So 10 minus 7 is 3. 333 degrees Celsius, so C. Question 6 shows 2 opposite point charges, P and Q. The force F acting on P due to Q and electric field strength E at P are shown. So this is the electric field strength, which goes positive to negative, and then the force always shows like an attraction or a repulsion. Which diagram shows the force on Q due to P? Right, well, let's look at the force first of all, before we get to the electric field strength. So the force, if P is moving or being attracted to Q, then Q must be attracted to P. So the force is going to be in that direction, which makes it either that or that. Okay, they can't both be moving in this direction. They will either be moving towards each other or away from each other. So it's either A or B. Now, the electric field strength, to get this right, you have to fundamentally understand what happens to field strength. Now, electric field strength is for a given situation, like in question 1, and that depends on the initial charge of the particle. So if we're going positive to negative, then it will come out of that charge. If we're going negative to positive, it will be going towards that charge. Now the field strength, E, is moving in this direction. Now that is not going to change at all. Okay, that is not going to change because we haven't got any other point charges there. So for this situation, the electric field strength is constant. So it is B. Question 7. We have a Fleming's left-hand rule situation. This is very much a GCSE question, actually, from topic 6 for Edexcel. So we have a simple current here, positive to negative. So we have the current. I like to draw in the arrows. As long as it isn't AC, we can do that. Okay. So we've got the arrows, and now we know the direction there. I'm actually going to remove these because there's no need. I'm just going to be looking at the current in this kind of big square area. So we've got a field north to south, and then we have a current going up here, across to the left, down, and then across to the right. And it's asking about the magnetic force, so the force acting on the sides RS, so this one, and ST, okay, and that one. All right. So the force, we know that we've got FBI. If you're a little bit rusty with that, check in your textbook, but FBI, we've got force, magnetic field, and conventional current. And then we just need to do the left-hand rule with our left hand. And if you do that, you would see that Fleming's left-hand rule for RS takes you out of the page. So this is going to come this bit here is going to come up towards you. And then on ST, because this is, because this current and these field lines are parallel and not perpendicular, there is no force acting. So the answer is B. Question 8. An object of mass m makes n revolutions per second around a circle of radius r at a constant speed. What is the kinetic energy of the object? Okay, kinetic energy, half mv squared. Now we know the mass is m, so we're satisfied with that. We need to know what v is. So if we have a circle and it has a radius r, we know that the distance covered is 2 pi r divided by the time to give it a speed. So, and it does, oh well, I'll come to that in a second. So Ke equals half m multiplied by 2 pi r over t squared. Almost. We have n revolutions. So that would be the case if it was doing 1 revolution in a certain amount of time, but this one is doing n revolutions, so don't forget the n. So let's work that through. Kinetic energy equals half m n squared, 2 squared is 4, pi squared r squared divided by t squared, where t is the number of seconds it takes. So we have kinetic energy equals half times 4 is 2. So we have 2m n squared pi squared r squared divided by t squared, and t is 1 because it's per 1 second, divided by 1 squared divided by 1 squared is divided by 1, so we cancel that out. So that's the answer. So I'm just going to locate that. I'm just going to check that this one is in fact correct because I've got them all in a slightly different order. Yeah, it's all there. I'm going to go for C. Question 9 is like a recall question. It's one of those ones you either know it or you don't. You must learn the assumptions of the ideal gas. There are several assumptions of the ideal gas, and you need to learn them. If you do learn them, the answer is C. Molecules suffer negligible momentum change during wall collisions. That is incorrect. That is what essentially causes the pressure upon the surface of a container from the force upon the area of the container. So it's C. Question D. A light source of power P is observed from a distance D. The power of the source is then halved. At what distance from the source will the intensity be the same as before? Okay, so intensity equals power divided by distance squared. The way I do this, I don't know how they teach it in maths, but the way I teach this is if you are dividing by something and you want to pull this out, what I do is the way I learned it at school was dividing by a fraction as easy as pi. You turn it upside down and multiply. So that's the way I learned it. So I learned it like that. Okay. So I would keep it like that for now. And now what we need to do is we need to say, okay, what happens if we halve the P? So if we halve the P, what we need to do, that essentially would go to 2 over d squared. All right, which then if you flip that back on itself, it's 1 divided by d squared over 2. And we want to know what that is in comparison to one of these. So hopefully you can see that if we square root, it's d divided by root 2. Okay, that one, I'm not sure if I've explained it the best way. That's the way that I learnt that kind of method at school, but it might be that one of your peers or another teacher might be able to explain it a little bit simply for you. So please do ask. Question 11 is an elevator question. Right, so we have a person standing on an elevator and the person's weight is 600 newtons. So say this is the person, the weight is 600 newtons. So let's say there is no acceleration in the elevator. Then the reaction force, the scales would read 600 newtons. Okay, so the scale is, so the reading on the scale corresponds to the normal reaction on the ground. Okay, so if a person, I'll do that again, if a person has a weight of 600 newtons, if the scale reads 600, it means the reaction is 600. Therefore, the resultant force is 0, therefore the acceleration is 0. So it means the elevator isn't accelerating. However, if the elevator has a scale reading of 900, doesn't mean that the person has suddenly gained weight. The person's weight is still 600. However, it means that the scale reading, the reaction on the ground, has now increased. So the net force, resultant force, is now 300 up, which means that the acceleration is 300 force divided by mass upwards. So acceleration is 300 divided by mass, which equals 300 divided by, if we assume that G is 10, so the mass is 60 kilograms. 60, divide that, 5, 1, it's 5 upwards. So the answer is D. Question 12 has a travelling wave on the surface of a lake. I'm just going to do a couple of wavelengths there. Has a wavelength of lambda. And I'm just going to highlight those just to make them nice and clear. 2 points along the wave oscillate with a phase difference of pi. In other words, 180 degrees. That's pi radians, 180 degrees. What is the smallest possible distance between these points? Okay, so if we take this almost like an upwards and a downwards, so to the right or to the left, all of this section, yeah, is in kind of the first half of the wave. All of this section is in the second half of the wave. So the smallest possible distance halfway between kind of a cycle is from here to here. So from here to here is pi over 2. So the answer is B. Question 13, we're moving through flux against time to EMF against time. And we're asking to recall this equation. Okay, so the EMF is the negative version of the change in flux over time. So we're going, it's like SHM, where you go from sine to cosine to minus sine to minus cosine. That would be kind of d something by dt. D something by dt, d something by dt, d something by dt. Okay, so as you move through differentiating, you go all the way back round in a cycle. So we are in a cos form here, and we need to differentiate. So we're going to differentiate cos, which takes us to minus sine. However, it's not minus sine, which is what I initially thought when I did this paper. I forgot that, in fact, it's minus sine. So it's actually this one, because it's minus sine, which is a plus sine. Okay, so don't forget the minus like I originally did. Okay. Right, question 14. 3 identical resistors, each of resistance R, are connected with a variable resistor X as shown. X is initially set to R. The current is 0.6 A. Okay. So these 3 resistors, so I'm going to call it fixed resistor, fixed resistor, fixed resistor, and then variable resistor X are R. These three are identical. This is not. Okay. When it's R, the current in the cell is 0.6, and it says what happens when X is set to 0. What happens to the current? Okay, before initially, all four of these have resistance R, and that creates 0.6 amps. So we need to find the total resistance in this section here in the circuit. So we've got resistors in series here. So we've got R plus R is 2R. So the first branch is 2R here. The second branch is 2R, and these two are in parallel. So we've got 1 over. So first branch in parallel with second branch, 1 over 2 plus 1 over 2 is a whole. So it's 1 over R. Therefore, R total in the circuit is flipped, which is R. So R equals 0.6 amps. Okay. This time, we are removing this one. Okay, so we need to work out what the overall is. So we have R here and still 2R in this bit. 1 over because they're in parallel. So now we have 1 over that, which is 3 over 2R. So therefore our total is 2R over 3. So now we've got 2/3 of the resistance. So you could say, if this is easier, 3/3 of the resistance creates 0.6, but now we're kind of negating 1/3 of the resistance. So it's going to be 0.90 amps, which is C. Question 15 is a rectification circuit. Conventional current in the load resistor actually goes in 2 half cycles. Okay, so the current passes through this one and this one at the same time, and then it will pass through this one and this one at the same time. So it goes in 2 half cycles. So actually what you get is you get a maximum twice in one oscillation. So you get a once, twice in one oscillation, once, twice in one oscillation, a bit like that. So actually it's A. I don't need to go any further. Okay. Question 16. P and Q are 2 moons of equal densities orbiting a planet. Right, so we've got density. I don't like the sound of that, so I'm just going to remind myself that mass is density times volume. I don't know any formulae to do with gravitational force, which I think this is where it's going with density in, so I suspect we're going to have to do something to that. The orbital radius of P is twice the orbital radius of Q. Okay, right, I'm just going to draw this out. I like drawings. So we've got a planet here, we've got a moon here, and we've got P is twice the radius in orbit, let's just say they're going that way, of Q. Okay, so let's say this is R, and let's say this is 2R, because this is twice that of that. The mass, we don't know. The volume of P is half that of Q. Okay, so if Q is V, then P is V over 2. And they have equal density. Right, so I'm just going to clean that up and put it into mass. So mass is density times volume. So if the volume is half, then the mass is half. So let's say this one is half the mass of Q. So P is half the mass of Q. So let's say P has mass M and Q has 2 of that because it's half of that. Okay. The force exerted by the planet on P is F. What is the one on Q? Okay. So force, we're going to have to use our formula booklets here if you don't know it. Is that. So let's plug it in. So F here, so F on P equals, I'm going to get rid of G because it's a constant, don't need any constants muddying the water here, equals my mass divided by my 2r squared, which is 4r squared, 2r all squared, 4r squared. So my FQ is 2m divided by r squared. I can see that if this is a quarter and this is 2, this is 8 times the force. So I'm going to go with that one. Okay, we've got phosphorus decaying into silicon. So we've got a reduction in atomic number, which means that we should have an increase in atomic number for this particle here. So that's a 1. 14 plus 1 is 15. 30, there's no change in mass number. So it's a 0. 0, 1, that you should know is a beta particle. You need to know that. Now that's a beta particle. Now that is an antiparticle, an anti-lepton. So that's an antiparticle. So if that's an antiparticle, that is going to be an electron neutrino. Okay, so we've got a positron, an anti-electron, a positron. So X is a positron. Oh, sorry. Okay, X and Y. It doesn't matter which way around you've got them. I always put the neutrino last, but they've already done it that. We're looking for a positron and a neutrino, so it's going to be D. Question 18 is looking for the speed of the wave. Okay, so speed is distance over time. Okay, distance over time taken. So if we look at these graphs, the key difference here is the x-axis. So this is time, so this is showing the period of the wave. So this is the period, and this here is the distance. So here we've got a wavelength. So we've got a wavelength over a period, so it's going to be RS over PQ. Question 19, which Feynman diagram shows beta plus decay? So beta plus decay is a positron to a neutron. So this is up, up, down, and this is down, up, down. So we've got an up turning into a down. So we've got an up going into a down, up going into a down, up going into a down, down going into an up. It's not D. And then if it's beta plus, we've got a proton going into a neutron. So the proton number is dropping by 1. So we're going to have a positron emitted and a neutrino. Oh, that's not a neutrino. Beg your pardon. That's a neutrino and not an antineutrino. I'll try again. A neutrino. So we are looking for these. This one is going to be coming in the opposite direction to time because it's an antiparticle. Antiparticles, so here, antiparticles go against time. That's how Feynman showed antiparticles on his diagrams. So we've got up, down, and then particle, yeah, and that's a W boson. It's that one, but let's just make sure that nothing else. So it's not an antiparticle, that's wrong, and that should be coming in that direction. This one, it's not a W minus. This copies the kind of the lepton. Okay, so if that's a plus, that will be a plus. So that's the incorrect bit there. So it's A. Question 20. Diagram shows atomic transitions. What is correct for these wavelengths? Okay. So we've got E1, E2, E3. I'm just going to write this. So we want wavelength. So we're not looking at the frequencies. So we're saying that E1 equals HF1, E2 equals HF2, E3 equals HF3. However, we don't want frequency, we want wavelength. So E equals HC over lambda. Okay, so I'm just going to remove these. Sorry, let me get rid of them. C over lambda 1, C over lambda 2, C over lambda 3. Okay, and we want to compare only the lambdas here. So here we have the largest E1. All right, E1 is the largest, which means that lambda 1 is the smallest. Okay, so lambda 1 is the smallest. Lambda 1, smallest. E3 is the largest, which means is the smallest, which means that lambda 3 is the largest because they're inversely proportional. Okay, so we're looking for lambda 1 is the smallest, lambda 3 is the largest. So it's not that, because that's saying the opposite. All right. Well, lambda 1, so these lambdas aren't related to each other like this. However, the 1 over is. So what I could do is I could say like that. Okay, so that is nonsense, all right, because it's 1 over lambda. So if lambda 1 is the smallest, then it's not this one, because here again we're adding together and we have to do 1 divided by, so it's not that one, which means it is actually D. And that's because we can see that E3 plus E2, this length plus this length equals this length. So we can say that E1 equals E2 plus E3. Therefore, HC over lambda 1 equals HC over lambda 2 plus HC over lambda 3. You could bring these out, these HCs, like that. There you go. And you get D. For question 21, we're looking at the velocities of two blocks that are being extended. To link the velocity to elastic constant K, we need to use this. Okay, whereby the maximum kinetic energy will equal the maximum elastic potential energy. So I'm going to go ahead and rearrange for V squared. Okay, so we've got two blocks, X and Y, and let's see what the differences are between them for each of the different values. We've got K, we've got X squared, M, oops, got a bit carried away there, and then V squared, and then ultimately what happens to V, so the square root of that. So we know that the elastic constant for both springs is 100, and they're initially compressed to a distance 0.1. So x squared 0.1 squared is 0.01. Be careful. Block X has a mass of 1, and block Y has a mass of 1/4. Okay, so if we multiply that through, so for the X values, we've got 100 multiplied by 0.01 squared. 0.01 divided by 1, so that comes out as 1. So V is 1. And then we've got 100 times 0.01, so that is 1, times by 0.25, so that is divided by 0.25. Sorry, I'm confusing you here. So we've got 100 times 0.01 divided by 1/4. So 1 divided by 1/4 is 4. So V is 2. So block Y is 2 and block 1 is 1. So C. Question 22, gravitational equipotential lines. So what we've got is we've got it moving towards the Earth. And in fact, if we were to rotate it like that, it would look a little bit more normal. So we've got a mass that is potentially kind of falling or being attracted to a large mass, okay, down here. So maybe like a planet or something. And so we can see it's accelerating down like that. Okay, so what is correct about the direction of motion and the acceleration? So it is accelerating because G is the value of the acceleration, the gravity. So the acceleration is getting larger. It's just getting more negative because it's attracting. That's all the negative means. So negative G equals attracting towards the mass. And so it's attracting to the left. So it is to the left increasing. Question 23, we have a wind generator and we have the speed of the wind flow is V, but then after it passes through the blades, it drops to V over 3, so it drops to 1/3 V. So we have the initial P is, we could say P, all right, and we know that the flow from our formula booklet is that. So P is proportional to V cubed. The only thing that it's saying is changing here is V. So the V is dropping to V over 3. So we could say that the P out is P in minus the P that is wasted. Okay. And P wasted is the fact that it's dropping to V over 3. So what happens? All right. So the wasted P due to V dropping equals half rho A V over 3 cubed, which is 27th, 1/27th. So that's P over 3 cubed, which is P over 27. So P out equals the initial P minus, so that's P in, minus the P that is wasted because the V has dropped. So minus 1/27th of P. So we are now only getting 26/27 of P. So the efficiency is 26/27 P over P. These cancel, so we get 26/27. Okay. 24, a kaon is made up of 2 quarks. If it's 2 quarks, that is a meson. 3 quarks is a baryon. Fundamental particle is a lepton. So exchange boson is one of the virtual particles, like a W plus boson or a W minus boson or something like that. A baryon is 3 quarks. Lepton is a fundamental particle, such as an electron or positron, and a meson is 2 quarks. And they will be a quark-antiquark pair. Okay, so a kaon will be a quark and an antiquark. Light is incident on a diffraction grating. For question 25, we are asked to work out the minimum number of grating lines that are illuminated. So this is to do with resolution. So resolution is the mean wavelength divided by the difference between the spectral line wavelengths, and that equals the order number multiplied by the minimum number of gratings. Okay, so let's go ahead and have a look at this. So we've got a mean wavelength of 590 and 2 spectral lines either side. So the mean is here, and we can say that the delta between them is 0.59. Okay, so we have 590 is the mean one up at the top, divided by 0.59. They're in nanometers, but they cancel, of course, so we don't need to convert. And that equals mn. Okay, where n is the 4th order. Okay, so 590 I'm going to divide through by n. Equals m. So 590 divided by 0.59 times 4 is 1000, divided by 4 is 250. Okay, Question 26 is a, thin film interference. Okay, so for thin film interference, it depends on what's going on. So if we are eliminating reflection, all right, if we are eliminating reflection, then the formula you want, and it is in the formula booklet, you just need to know which one to use when. Okay, so if we are eliminating reflection and we're going from a single interface, so we've got a liquid glass interface, so we've got a single phase change and we are eliminating reflection, okay, then we want this formula. It is confusing in the data booklet. It would lead you to think you want the other one, but you don't, okay? Just trust me on this, you don't. So, right, so we are going to figure out what numbers we want. So, a transparent liquid film of refractive index 1.5. So 2D is the thickness, all right, it's the thickness. N is the refractive index, okay? So we've got 2 multiplied by 1.5 multiplied by the thickness, which was what we're being asked, equals M, and we're asked for the minimum. So that means that M is going to be 1, the order number is going to be 1. We just want M to be 1. So that's going to be kind of for the initial. So M is negated. We don't need M, all right? So we're just going to have the half on here times by lambda. So that means that 3D equals half lambda. So D is a 6th lambda. So it's one of these. Now this column is saying for phase change. Now you just need to learn this as well. If you are going less dense to more dense, it's a pi phase change. All right, if you're going less to more, you get a pi phase change. If you're going more to less, you get a 0 phase change. So it's this one. So the answer is D. Albedo, it's saying albedo is 0.1. What does albedo mean? Okay, so a recall answer here. Albedo equals, so if it's 0.1, that's saying 10%. All right, so that's like an efficiency type thing. So it's saying the percentage of radiation incident on a body is reflected. So it's saying how much, what percentage of radiation that is incident is reflected by its surface. So incident absorbed, incident reflected, here we go. Okay, so 10% of the radiation incident on the moon is reflected by its surface. So it means that 90% is absorbed by its surface. Question 28. We've got monochromatic light coming through a diffraction grating. n lines per unit length. Okay, so we've got a diffraction grating, so I'm going to go ahead and write the formula because I think I'm going to use it. Okay, I'll put a θ1 here because they've put a θ1. Okay, so I'm just copying their language. The angle between the first orders is θ1. What is the wavelength? So we're just going to go ahead and rearrange. Okay, so it's d sine θ1 divided by n. Okay, so we are looking, they don't want the d, they're just looking, so we've got, I'm just trying to find it. I want to say it's A. I've missed something. Ah, I know what I've missed. Fool. Right, I've fallen into the trap. What have I done? I bet you're all screaming at me right now. What have I done? They have given us... Oh, that's sneaky. Sneaky. Mrs. Hyman fell into the trap. They have said that θ1 is all of this. So it's from this one to this one. But of course it's not. We've got the central maximum there. And the angle is always to the central maximum. So these angles are the same. But it's to the central maximum. So... Silly Mrs. Hyman. I can't believe I did that. Right, there we go. Happier now. All right, so we're going to go ahead and try one more time. D sine θ1 over 2, all divided by n. That's a weird looking n. So θ1 divided by 2 divided by... Right, D. Okay, better. Question 29 has a single slit diffraction pattern. And it's asking for the ratio of wavelength of light to width of slit. Now, the way to answer this is to know what that is as a formula. So the wavelength of light divided by the width of the slit equals theta in radians. So if we look here, we can see that theta to the first order is 10 to the minus 2, which doesn't appear. Now that is the answer, but that doesn't appear in the answer, so we need to convert that. So it's 0.01, so the answer is A. Question 30 is looking for the escape speed of an object, okay, from the surface of the Earth. So escape speed is located in the data booklet, as are most of these things. And that is the formula. Okay. So let's go ahead and see what we can plug in. Now, first of all, if we're looking for the escape speed, that is the answer. But we can see that if we look in the answers, we're missing the capital G. So we have to substitute something in for the capital G. Now, the easiest way to do this would be to find a formula that links little g and capital G, the gravitational constant, and the other symbols that we have. And I would go with that one. In fact, that's the one you do need to go with. So I'm going to rearrange that for G and then plug that into there. Okay, so G equals GR squared over M. And then I'm going to plug that into my escape speed one. So I've got 2m times by G, big G, which is little g r squared over m. divided by R. And so I'm going to cancel those out. I'm going to cancel one of these out, and I should be left with 2GR. Oh, idiot. I forgot to square root it. Okay, so it's root 2GR. So it's B. Okay, so exactly as I said, apologies, I just missed out when I was substituting all of this. Initially, I forgot to put that square root in there, which has appeared here. So exactly what I said before, just apologies, I forgot to drop the square root all the way through. Okay. Right, question 31 is another kind of orbit question. A satellite orbits planet X with speed Vx at a distance r from X. Another satellite orbits Y at Vy at a distance r from Y. Okay, so the speed of orbit is root gm over r. So in the previous question, the escape speed is root 2 gm over r. So it's a factor of root 2 bigger than the v orbit. So v orbit, I should say v escape equals root 2 times v orbit. That's what you have to do. So you have to go a factor of 1.4 approximately bigger than the orbit speed to escape the orbit. All right, just out of interest, but that's not relevant for this question. But that's the link. Okay, so v orbit. So let's have a look and see what's going on. So we need to know Vx over Vy. So let's work out what each one is. So Vx equals root g. What is the mass? Planet X has a mass of m, and it's orbiting at a distance r. All right, simple enough. Vy is g. I don't need the g's. Mass is 4m, and at a distance r as well. Okay, so we can see that Vy is root 4. This is crept in. Root 4 times bigger than Vx. Okay, so Vy equals root of 4 is 2. All right, so we've got Vx divided by Vy, which is 2 Vx. So we've got 1 over 2, so that's a half. So it's B. Okay. Now, question 32. You could do a load of calculation, but the easiest way to do it is just through looking at kind of the simplest link in Year 10 GCSE, what you know about current through a series and parallel circuit. So if we think that current is the flow of charge, we can kind of link the idea of current flow through Z, and then current flow through X to charge stored. Okay, so if we've got current flowing through, let's say it's conventional, if we've got the current flowing through here, we've got the whole current through here. They're all identical capacitors, so we're going to have half the current flowing through here, so half the charge here, and then half the current flows through here, half the charge. And then when it gets back to here, through Z, we've got the full current flow. So kind of double kind of the charge of X. I'm sorry. Okay, so basically the charge through Z equals double whatever flows through X. Or you could say the charge through X is half what flows through Z. So we are literally looking for a row where Z is 2 times X. Okay, that's what we're looking for. So Z and X are the same. It's not that one. It's saying here that you've got double the charge flowing through X than Z. Well, that's not correct because we've got half the charge, so that's not correct. C, we've got double, so we've got 2/3 and 1/3. So we've got double the charge flowing through Z than X. That is correct, but for good measure, let's just check. And then we've got equal charge flowing through these. Well, that isn't correct because X and Y are shared from Z. So it's not that one. So it's C. That is the quickest, simplest way to do it. Just strip out all your calculations. Just go with basic Kirchhoff law. Okay. 33, we are looking for fundamental SI units of X and Y. Okay, so a student models the relationship between pressure and its temperature. Okay, so we've got pressure equals something plus a gradient times Kelvin. All right. So if we've got, I'm just going to rewrite this here. Okay, so we've got y-axis equals gradient times x-axis, and x is where it crosses on the y-axis. Okay, so it's the y-intercept. So it's going to have the same units. Okay, it's going to have the same units as P, pressure. Okay, so we need to work out what Pascal are. So here we go. So Pascal equals newtons per meter squared. Now you might know these off by heart. It's a good thing to kind of know off the top of your head what newtons is and things like that, just to save you time. But I'll work it through. So newtons is mass times acceleration. So it's mass times acceleration. So I'm going to actually write it like this. And then meters squared, mass times acceleration. Okay. So they cancel. So it's kilograms per meter second squared. That's your pressure. And then your y is your gradient. So it's kilograms per meter per second squared divided by, because it's pressure divided by temperature. So it's kind of pascals per Kelvin here. So it's pascals per Kelvin. So it's going to be this one. So the answer is A. Okay. 34. The root mean square speed, sorry, not speed. The root mean square current in the primary coil of an ideal transformer is 2 amps. Okay. The RMS voltage in the secondary coil is 50 volts. The average power transferred is 20 watts. What is NP over NS? Okay, so we need to know NP over NS. Now, NP over NS is equal to IS over IP. All right, I think that's in your formula booklet. But you have NP over NS equals VP over VS equals IS over IP. That's how it goes. All right, so the I's actually flip. All right. So this is what we need. So we need to. So if we plug these in, we know that the current in the primary is 2, but we don't know IS. All right. However, we know that P equals IV, and so we can rearrange, because we know that the average power is 20, and we know that the voltage is 50. All right, so that's 0.4 amps. So that is 0.4. So 0.4 into 2, so it goes 0.4, 0.8, 1.2, 1.6, 2. That's a fifth. Okay, so it's a fifth, and average power transferred. Power transferred is we assume it's 100%. So the power transferred doesn't change if it's 100% efficient, and it doesn't tell you that it's not. Oh, it's not ideal. Okay, so it's 100% efficient. So that's a bit of a trick. So it's this one. I see. Okay, question 35. A train approaches. Right, a train's approaching. Sounds a horn of constant frequency and constant intensity. An observer waiting detects a frequency obs and intensity obs. All right, well, if it's approaching, here is my awesome picture of a train. Just going to draw some windows. Why not, hey? It's approaching an observer. If it's approaching, the intensity, the volume of the horn is going to increase. All right, so the intensity is going to increase. And the frequency observed. So the frequency observes. So that we need to know what the train is doing. Is it okay, right, so it's slowing down. So the frequency, the change in frequency divided by the correct frequency is approximately equal to the speed divided by the kind of corrected speed. So if it is slowing down, the speed is dropping. So V is dropping, which means that the change in frequency is going to drop, which means that the frequency is dropping. Okay, so if you are increasing speed, if it was accelerating, it would be increasing. If it's decelerating, it is decreasing. So it's D. What have I done? What have I done? Oh, I've done that. Bear with me. Let me just sort this out. Question 36 is another EMF flux question. This time they're asking for the phase relationship between flux and EMF. So EMF is negative d phi by dt, where phi is flux. So it's one of those ones where we're going from sine kind of to cos to minus sine type thing, except we've got a negative here. So sine actually goes to minus cos, and then minus cos. So cos would go to minus sine, but it doesn't. It goes to sine, etc. So we are going from a sine to a cos shape. All right. This one doesn't. That's sine to sine. That is not correct. This one goes from sine to minus cos. So that one is correct, and it's going to be the answer. This one is going from a cos to a sine. So it's, hang on, cos to a sine. Oh, no, it's not. Yeah, sorry. It's not. It's going from a sine to a cos. So it's flux to EMF. So this one is sine going to cos. That is not an option. All right. That is not an option. So that's not that one. And then this one is sine to minus sine. That's not an option either. So it's B. Question 37, a Unit 1 question. Okay, percentage uncertainty of density. So percentage uncertainty is equal to, we've got a mass here, and we've got a length of a cube, so therefore we can work out the volume. So density is mass times volume. No, it's not. Forget that. Density is, yeah, it is. Hang on. Is it? Density is mass times volume. Density is mass times mass divided by volume. Sorry, I'm losing my mind. Right, doesn't matter anyway. So we've got the change in mass plus the change in volume. All right. So the change in mass is 8 as a percentage plus the change in volume. So volume is length times length times length, which is 3L. So it's 3 times 4. So it's 8 plus 12 equals 20. Okay, question 38. Specific heat capacity. Okay, right, we have a piece of metal. We've got two substances here. So we have a piece of metal, and that's dropped into some water in a container. We know that the energy kind of supplied by the very hot metal is going to go into the water. Okay, so until it reaches equilibrium. So Q equals mc delta T. I'm not sure if it's Q. I always say this when I'm teaching it. I don't know if it's Q or E in the data booklet. It varies from GCSE to IB, and that's just in physics. And then in Key Stage 3, we teach another thing. in chemistry, and then IB chemistry might be different, and yeah, so there's loads of different ways of saying it, but Q is heat energy ultimately. So it's the energy equals the mass multiplied by the specific heat capacity, the amount of energy in joules required to heat up a unit mass by a unit temperature, multiplied by the change in temperature. So I'm going to go ahead and write that out. So we've got a delta T here, so a change in temperature, and this is for the water. We've got one temperature minus the other. All right, and I'm going to now plug in the correct numbers. Okay, so a piece of metal at a temperature of 100 degrees, at 100 degrees, is dropped into an equal mass of water at a temperature of 15. So for this to work, this number needs to be positive, and this number needs to be positive, because we can't have a positive equaling a negative. So we have to work the numbers inside the brackets, put them in the correct places so that they work out positive. All right. So it starts off at 100. So we've got, like, if we think about the thermometer here, all right, we've got the metal, we've got the water, and then the metal is going to be submerged in the water. The metal is going to cool down, and the water is going to absorb that heat until it reaches kind of a final equilibrium temperature. All right. So this is going to be the highest. This is going to be the lowest, and then this is where it's going to settle. All right, our temperature final. So the metal is going from 100 to the final temperature, and the water settles at a high final temperature from a low temperature. So I've put the 15 there so that a big number minus 15 is going to give me a positive number. Okay, if I put it the other way around, if I say 15 minus, I don't know, say 40, I'm going to get a negative number, and it's going to mess with me. All right, so let's keep it like that. So let's figure it out. They've also said, which I just saw, negligible not negligible mass, ignore that, equal mass. So we can cancel these. All right, we can cancel these. So, and we'll do that in a second. So the specific heat capacity of the metal, what's the specific, we're not given numbers, but the specific heat capacity of water is 4 times that of the metal. So I'm just going to say, if C is for the metal, then 4C is the water. It's 4 times the metal. So if the metal, if the metal is C, the water is 4C. Okay, so I've just kind of dropped that in there. Okay, and let's just do a little bit of multiplying out the brackets. C times 100, 100C. C times TF minus TFC. Sounds like a boy band, doesn't it? Right, and then 4C times TF, 4 TFC, minus 60, 4 times 15, 60C. Okay, let's get everything on the right side. So 100 plus 60C equals, I'm just going to put 5. So 160 C equals 5 TFC. I can see C's on both sides now, so I'm going to cancel. That's nice. And so we're trying to find TF, which is 32. 32. It's in degrees Celsius. I don't need to convert. Lovely. Okay, 39. Oh, my favorite kind of question. They always come up. Funny that. Right. Water is draining from a vertical tube that was initially full. The vibrating tuning fork is held near the top of the tube. For 2 positions of the water surface only, the sound is at its maximum loudness. The distance between the 2 positions of the maximum loudness is x. Okay. What is the wavelength of the sound emitted by the tuning fork? Right. So, okay. So we know that when you've got a standing wave, there's going to be positions of antinodes and positions of nodes. At nodes, there is 0 vibration. And of course, sound wave requires vibrations so that we can hear the sound wave. If there are no vibrations, in other words, if you're at a node, no vibrations, you get silence. Okay. If you are at an antinode, you have maximum vibrations, and therefore you have maximum loudness. Okay. I should write maximum. So we know that at X, here, and I'll do it here because it will be cleaner. We have antinodes. All right. So what we need to do is we have to get like that. That's actually a terrible drawing. It's going to go like that. Yeah. So we would carry it on like that if it was still like that. And then I'll do this one in another color so you can see it. So the reflection is going to be like that kind of thing. All right. So we can see that this is lambda over 2 because we're going from crest to trough, so to speak, where this is your reflection. Okay, so one wavelength is going to be double that, so it's going to be 2x. And then the final question. I've got a bit of Kirchhoff's law. Okay. Right. So we have identical cells. Identical cells. So each cell has an EMF of 5 volts. Okay. So firstly, if these two are in parallel, then the cell overall, sorry, let me start again. What you could do is you could actually say that this is just one big cell like that, and that indeed these don't exist. So if we can say that the internal resistance of this one is 2 and the internal resistance of this one was 2, then the overall resistance is going to be 1, because you've got 1 over 2 plus 1 over 2 is 1. over 1 equals 1. So the overall resistance of this one is 1. And if the cells are in parallel, then in fact you only get the EMF of one of those cells. So we have 5 volts. So the current that is running through is going to be 5 volts divided by, we've got 1 ohm here and 4 ohms here, so we've got kind of 4 plus 1, so 5 over 5, that's ohms, and that's what's in the circuit, which is 1 amp. So the answer is A.